He won an award for being the most studious. He is from Togo. I think you know what I'm talking about. Yeah. Herman, Akagla.
My name is Herman, Akagla. I will present in quantum field theory. My topic is Noether's Theorem. This is my outline. I will start with the introduction, description of symmetry, the proof of Noether's Theorem, and conclusion. Who is Noether? Noether was an influential mathematician known for her groundbreaking contribution to abstract algebra and theoretical physics. Remember, Noether is a German mathematician. The statement of the theorem. Noether's theorem states that every differentiable symmetry of the action of a physical system has a corresponding conservation law. Historical context. The theorem was proven in 1915. In 1915, her mother died. So she waited, and in 1918, she published the theorem. The action of a physical system is the integral over time of a Lagrangian function from which the system behavior can be determined by the principle of this action. In physics, the symmetry of the physical system is a physical field that is preserved or remain unchanged under some transformation. Example, the invariance of the form of physical law. And the second example I can add, you see in the course of quantum field this block, is the invariance of the speed of light in all frames. Local and global symmetry. Symmetry may be only classified as global or local. A global symmetry means we do the same transformation at all points of space-time, whereas a local symmetry is one that has a different symmetric transformation at different points of space-time. Conservation law and symmetry. The symmetric property of the physical system are intimately related to the conservation law characterizing that system. Noether's theorem gives rise a precise description of this relation. Example, the isometry of space gives rise to conservation law of linear momentum, and the isometry of time gives rise to conservation of energy. The following table. So you have a simple table here. In the first column, you have the class, invariance, and the concept quantity. When I take the pointary symmetry, with pointary symmetry, you have the rotation, the translation, and the boost. Okay. So here we have the translation in time. The translation in time gives the conservation of the energy, and the translation in space gives the conservation of the linear momentum. If I take the Lorentz symmetry, the rotation in space gives the conservation of the angular momentum. So the only thing you need to know after this presentation is the relationship between the symmetry and the conservation law. The only thing you do the relationship. This theorem is to put the relationship between the symmetry in the nature with the conservation of the nature. So the role of symmetry in field theory is possible even more important than in particle mechanics. There are Lorentz symmetry, internal symmetry, gauge symmetry, supersymmetry. We start here by recasting Noether's theorem in field theoretic framework. So every continuous symmetry of the Lagrangian gives rise to a concept QS such that the equation of the motion implied in equation 1. So this we write it in 4 vector notation. So the second equation you see here is the notation in 3 vector. So we will prove the theorem like we do in class by working infinitesimally. You may always do this when we have a continuous symmetry. So here we use phi prime equal alpha x plus alpha delta phi, where alpha is an infinitesimal parameter and delta phi is some deformation of the configuration. So here we use the Lagrangian density L prime equal Ls plus alpha delta. Okay, to derive Noether theorem, we first consider making an arbitrary transformation of the field. So here we have alpha delta phi. Here is a lot of calculation we do in class. So here you can see we have f nu plus alpha and the term in the bracket. When the equation of motion are satisfied, the term in square bracket, you will remember this is the Euler Lagrange equation. Okay, so we have alpha delta f is our equation 7. Okay, but for symmetric transformation, we have by definition delta L who give us the equation 8. And equating equation 8 and equation 7, we have this result generally, which satisfies the continuity equation in 4 vectors. Or in 3 vectors, we have this. The corresponding Noether chart is given by Q equal integral of generally. Substituting equation 11 in equation 10, we have this equation. And we see in class that this equation vanished in the boundary of the field. Okay, so this is 0, you have dq over this equals 0, so Q is conserved. Okay, the rotational invariance. The conservation of the angular momentum L equal R plus P is analogous to linear momentum counterpower. It's assumed that the symmetry of the Lagrangian is rotational. So here we use R plus theta times N plus R. So taking delta phi as the small parameter epsilon and Cartesian coordinate R, we can generalize Q like this, N Q equal N plus R. So Noether theorem states that the following quantity is conserved. You have the partial derivative of Q over dq dot equal N plus R. In other words, the component of the angular momentum along the N axis is conserved. So if N is arbitrary, then every component of N is conserved. In short, the angular momentum is conserved. So you will use this to write the matrix. Okay, so we have this equation is prime and so on. So because Z is fixed. Okay, since the Hamiltonian has an invariant property, we accept the conservation law. To identify the operator that commutes with H, let us consider an infinitesimal rotation about the Z-axis. So theta is very small, so cos theta is 1, sin theta is theta. We just substitute, we get this equation. We get that H times our wave function equal this. So if you expand to the first order in theta, we get the equation 12. We obtain from the term in linear theta, we obtain this equation. We just transform this equation, we obtain this, and we have the equation 14. So if we define the angular momentum Sz is equal to h over I x x minus y cubed. So you can have, if you use equation 13 and equation 14 together, we have the commutator HLZ minus LZ. So we have the commutator between H and LZ, which is 0. LZ, the component, the Z component of the operator L plus R. So had we taken the rotation about X and Y axis, we will find in addition this commutator. So visual interpretation. That's the key component of the angular momentum operator commute with the Hamiltonian. That means that the angular momentum is a constant of the motion. To summarize, if H is rotationally invariant, then the total angular momentum is conserved. This is an example of Noether's theorem. So in conclusion, Noether's theorem states that every conservation law is associated with symmetry. The symmetry associated with conservation law of angular momentum is the rotational invariance. The fact that the physics of a system is unchanged, it is rotated by an angle about an axis, implies that the angular momentum is conserved. Application. The application of Noether theorem allows physicists to get powerful insight into any general theory in physics by just analyzing the various transformations that will make the form of the law involve invariant. So this is my reference. So this is my code. Yesterday is your, don't know, your international, so it's for you who are
Thank you very much, Herman, for that nice presentation.
Yeah, I will teach you. Don't worry.
We have a seat like this and he has not been wearing it to us. Any questions? Yes.
So maybe I overheard that. Did you say what conserved quantity corresponds to Lorentz boosts?
Lorentz?
You said counter symmetry at the beginning. You said,
okay. Talking about the pointary symmetry, you have the rotation, the translation, and the boost.
Yes. And then you said, okay, translation that gives us conserved momentum. I understand that. And rotational symmetry gives us angular momentum. That I also know. So what do the boosts give us? There should be some conserved quantity now, which corresponds to the boosts.
No, I didn't put the boost here.
But you see the boost. You say the boost. Remember you said you say boost. So what is the boost? No one.
Anyone else have any questions? Any other questions?
My friend. Hmm? Yes, video.
Okay, in the absence of further questions, let's give it up for him. At this juncture, we would like to take a 10-minute recess to prepare for the next part of the presentation.